Alrighty, so what we're talking about today is periodic trends. And you read about some periodic trends both in the activity that we did yesterday in class and then in your homework last night as well. Again, if there's some things in your homework you didn't get, don't worry about that. We'll go over both of those things, last night's homework and tonight's homework, which to be honest, you'll get it done during class. We'll go over that all on Monday, so we'll kind of recap everything on Monday. So the whole reason that we can predict trends going across and going down is because of this thing called periodic law or periodicity. A couple students have already shared their lab with me, and they mentioned about periodic law or periodicity in their intro for the lab. Because remember, in the lab we were looking at alkaline earth metals, and why do alkaline earth metals behave the same way? Okay, what? Same group. And what do groups have in common? Every member of a group has something in common, right? Well?
Same number of electrons in the outer.
Same number of electrons, excellent, in the outer ring. And what do we call those electrons in the outer ring? We know there's really not rings, but what do we call those electrons? What? Valence electrons. Okay, and now that you are graduates of electron configuration, we're actually going to have outer ring was great prior, but now we've graduated, and we're going to say that valence electrons are the highest order S and P. They have the highest order S and P. So, like how, you know, you learned about the rings, right? You can have 2, and then 8, and then 18, and then 32. Which you would consider valence electrons if you were looking at the Bohr model with the rings. But when we talk about, say, iodine, for example, iodine has 7 valence electrons. Even though if you were doing the Bohr model with rings, it would have a lot more. But again, when we're talking about valence electrons, we're just talking about the highest order S and P. Now the other thing that you're going to realize as I'm going through this today is that the first one is going to take it, the first trend will take us a little while to process and go through, but you're going to find that the reasons for the trends are all going to be the same, and to be honest, it all has to do with attraction. Now yesterday in your packet I told you not to worry about this word, but what did they call it in the packet? What was the word that they called it in the packet that I told you didn't have to worry about? Coulombic attraction, and I'm going to call that something different. In fact, I'm going to skip down on your note sheet. Did you all see that I gave you a note sheet? It just might be a little bit easier. I'm calling it something different. I'm calling it effective nuclear charge. So let's write down those definitions. Effective nuclear charge, or like the packet called it Coulombic attraction. This whole lesson is all about attraction between the nucleus and the electron. So, and that's what this is. Effective nuclear charge is the attraction between nucleus and electrons. Then I'm going to give you one more definition and then we're going to get into it, and that's called shielding. Well, I'll explain more about shielding as we go through the specific examples, but shielding is the inside electrons, and it's easier if you think of it as rings. So you have the nucleus, and then again, if you think of it as rings, and then we have the valence electrons, those inside layers are blocking. Just like if you take 2 magnets and you put something in between them, it's blocking the attraction. Okay, so that's what shielding is, and you should have read about shielding last night. So the first property that we're going to talk about is atomic radius. Now, it may seem weird to you because like an atom doesn't have an edge, right? So how can you measure like from the center of the atom to the outer edge if it doesn't have an outer edge? So let me give you a definition of what I'm referring to for atomic radii. It's going to be half the distance between two nuclei. Okay. So let me kind of draw a picture. So if this is a nucleus, and then here are the electrons, but you know, we don't really, again, we don't know where the edge is. So the atomic radius is half the distance from the nucleus to the nucleus. That makes sense. Okay, so the first thing we're going to talk about is going down the periodic table. And I'm going to just draw down the arrow. Yesterday you guys had a little bit of trouble with those, you know those pictures of the periodic table on the packet that I passed back today? It looked like the arrow was going in the wrong direction, like the arrow was pointing up, but yet you're going down the periodic table. So what I mean by this is, okay, so we're going down the periodic table, what happens to atomic radii? This one is really easy to understand. Every time you add a principal quantum number, you add an energy level. Each subsequent energy level gets farther and farther from the nucleus. So think about it as from electron configurations. We're going down the periodic table, you're adding energy levels, right? And so what's going to happen to the size of the atom? Yeah, it's going to get bigger, exactly. So as you're going down the periodic table, it increases. And then for the Y, why did you say? Can you someone summarize that? Why that is? Why does the atom get bigger as you're going down the periodic table, Brandon? Right. More energy levels. And again, I understand that the Bohr model is obsolete, but it's fine to be thinking about it in terms of the Bohr model because I think that makes it easier to understand. The part that's actually, I think, a little bit more confusing is what is the trend when you're going from left to right? It seems like you're adding stuff, right? As you're going left to right, the atomic number's going up. So you're adding number of protons, you're adding neutrons, which don't matter, or you're adding electrons. So you're adding stuff. It kind of seems like if you're adding stuff, the atom should get bigger. But it actually doesn't. It gets smaller. And does anybody have a reason why that might be? Why, if you have more protons and you have more electrons, why is the atom getting smaller?
Is it maybe like if there's more electrons, it's like a tighter hold on the nucleus?
Exactly right. I think about it as like little, like ringed piles of magnets, right? If you have a little pile of magnets and a little pile of magnets, there's some attraction between them. You have a bigger pile of magnets and a bigger pile of magnets. Isn't there greater attraction? And I like the way Will said that, it's like it's more compact, so it's definitely going to be more dense. So in terms of the definitions that I gave you, can anyone use one of these definitions to explain why the atom gets smaller going from left to right? I also think Julia's raising her hand, but she's really not.
It has a greater effective nuclear.
It has a greater effective nuclear charge, right? It decreases because there's greater attraction between the nucleus and the electrons. All right, got it? So let me, we're gonna have a quiz, probably not on Monday, but probably on Tuesday after we go over your homework. And the quiz is gonna talk, it's gonna be easy because you're not gonna have to do any of the whys. You're just gonna have to say, for example, right now, if I said which is bigger, beryllium or strontium, what would you say? Which is bigger, beryllium or strontium? Strontium is bigger. If I said which is bigger, magnesium or chlorine, what would you say? Magnesium. Okay, so that's the kind of questions that I would ask on your quiz on Tuesday. All right, the next definition is ionization energy. And you should remember this from your packet. It's the amount of energy it takes to remove the most loosely held electron. Now, the most loosely held electrons are always going to be in that valence sublevel. So it's the amount of energy needed to remove Can you read my cursive? The amount of energy needed to remove the most loosely held electron or electrons. In a minute, I'm going to talk about there's something called first ionization energy, second ionization energy, third ionization energy. So you're going to see what that is in a minute. Okay, as you're going down the periodic table, we know those valence electrons are getting farther away, right? Does everyone ever, you got to know that solid, right? As you're going down the periodic table, the valence electrons are becoming farther from the nucleus, right? So is it going to be easier or harder to lose those electrons? It's going to be easier. So let me give you an example. So let's say, actually, can you for today just think of me as the nucleus all day today? Just nucleus. In Jordan, let's say she's a 1s electron, okay? So there is, I'm holding on to her pretty tight. Now let's say that Jacob is a 6s electron. Which electron can I lose more easily? Jacob's. He's farther away, but there's another reason why I can lose his electron more easily. And there's this vocab word is on the board. What's another reason I can lose Jacob's electron more easily, Brandon? Shielding. Not only is Jacob farther away, but Emily and Julia and Eugene are blocking my ability to hang on to Jacob, right? Okay, so there's less attraction between the nucleus and the valence electrons for Jacob than there is for Jordan. So to say it's easier is a way, we would say that ionization, it takes less energy, that's the way to say it's easier. So ionization energy decreases as we're going down the periodic table. And the reason, there were two reasons. What are the reasons? Shielding, and what was the second reason? Farther away. Shielding and distance. Okay, as we go across the periodic table, nothing's changing with distance, right? Because you're filling electrons into existing energy levels. Everyone agrees with that? I'm coughing because I have a demonstration to show you, which I practiced before school, realizing I really should have done it in the hood, and it's still, I have the ventilation on, but it's still, I'm coughing just from doing it, so I will do it for you in the hood later on. And I discovered something else about this demonstration as well, which I'll tell you later. But it really hurt my throat. Okay, so as we're going across the periodic table, so what's happening? The atomic number is going up, which means that there's more protons. So as you're going across the periodic table, I, as the nucleus, right, keep getting more and more positive. So the greater my positivity, that's not really a good word, letter is effective nuclear charge, I'm going to have a stronger hold on those electrons, which are all the same distance away. So it's going to be harder to lose. Do you guys agree with that? Okay, so what would we say about ionization energy? It increases or decreases going from left to right across the periodic table? Increases, right? And the reason is increased attraction. Can I just put increased attraction, or do I have to put between the nucleus and the electrons? That's always the attraction. What? I can just put that, we're good? Okay, now, things are going to get a little tricky for a moment. I'm going to and I'm not even going to write anything down about this, but there's different levels of ionization energy. There's first energy, ionization energy, second ionization, third ionization. So let me Okay, so let's think about this for a minute. Just tell me easy or hard, what would you think? So, would you think that potassium would lose an electron easily or not?
Yes.
Yeah. In fact, we know if it loses, potassium loses an electron, it's like, what noble gas? Argon. Now, when it had 19, it loses one, it has 18. What about the second ionization energy? What that means is the amount of energy it would take to remove the second electron. Would that be easy or hard? Hard, because it's like a noble gas already, right? You don't mess with the noble gases, that's why they're noble. Okay, let's think about calcium. Would it lose its first electron very easily? Yes, it would. Would it lose its second electron very easily?
Yeah.
Yes, it would. So it would have a low first ionization energy, a low second ionization energy. But what about the third electron? When it loses two, again, now it's like argon. So is it going to be easy or hard to lose the third electron?
Hard.
Hard, okay? So that's all. It's not more complicated than that. But remember, once you lose enough electrons to become stable like a noble gas, then ionization energy is really high. So that makes sense that it would be like that for the noble gas. Okay, the next trend we're going to look at is electron affinity. And let me write it first. Okay, electron affinity is the ability of an atom to snag a stray electron. I put similar to electronegativity because your book talked about electronegativity, as did the packet that I passed back today. Electronegativity has just such a subtle difference, which really isn't even important to me. But electronegativity and electron affinity both are the ability of the nucleus to pull on electrons, okay? Electronegativity is when two atoms are bonded together and there's electrons in between them because they're sharing electrons. Which nucleus is pulling greater, okay? So it's pull on electrons but within a bond. Where electron affinity refers to the pull of an electron, just a single atom pulling on some stray electron. So like you would think of it as becoming a negative ion. How does an atom become a negative ion? By gaining an electron, right? So that's more what I'm referring to. But they're so similar, the trends are the same. So I just want to make sure that sometimes I make a mistake and I'll use one instead of the other, but pretty much they're the same thing. Okay, so again, now you're going to be able to start to predict these patterns for yourself. As you're going down the periodic table, Jacob didn't like when I used him as an example. I'm the nucleus. Dan has a stray electron. Joey has a stray electron. Whose electron am I going to be able to get more easily? Dan's. Why? Because he's closer, right? Okay, so as you go down the periodic table, it gets more difficult to grab an electron because there's less pull. Why? Further apart. Okay, so you're starting to see a pattern here, right? So as you go down the periodic table, electron affinity decreases. Again, it's due to distance and shielding. As you go across, I'm really writing shorthand, and hopefully that you're writing, that's why I gave you the note sheet, thinking that it would be more helpful than the tricky scratch I'm doing on the board. But as you're going across the periodic table, again, the atomic number is going up, so the nucleus is getting more positive, so it's got a greater pull, so you're more able to grab an electron. So same as ionization energy, electron affinity increases as you're going across the periodic table due to, can I just say attraction? You can call it effective nuclear charge, but of a greater attraction. reactivity is gonna be kind of weird, because for reactivity, there's actually two different patterns. How did I do this one? Okay, there's two different definitions of reactivity, and there's two different trends for reactivity. First of all, for metal, the definition of reactivity is the ability to lose electrons. Okay, metals lose electrons, non-metals gain electrons. Let's talk for a minute about the stair step. And remember there was a column, and you guys asked about this at the time, like the carbon family. Do you remember what we had as a heading for the charge for the carbon family? Plus or minus 4, and you guys often said, well, which is it, plus or minus 4? How do we know? Well, now you know. Because metals are always going to lose electrons, non-metals are always going to gain electrons. So for example, silicon, what would charge with silicon for?
+4.
-4, right? -4 because it's a non-metal. You might not be able to see it, but here's the red line. So silicon is on the right side of the line. It's a non-metal, so it's going to gain electrons. What about the charge on tin? +4 because it's a metal. Okay, so now that's how we know. So the trend, as we're going, and then I have a demonstration to show, as we're going down the periodic table, is it easier to lose or harder to lose? It's easier to lose, right? So what happens to reactivity? As you're going down the periodic table, it's getting easier to lose. What? Increases, very good. And as you're going across the periodic table, is it easier or harder to lose? It's harder, right? It's harder. So reactivity, so we're going to be less likely to lose. So reactivity is going to decrease. Non-metals, it's just the opposite. We're going to go through some examples in a second. As you're going down the periodic table, remember the definition is different. For non-metals, it's our ability to gain electrons. So as you're moving down the periodic table, say for example in the halogens, which if you don't know the name of the halogens, that's okay because we're going to learn that on Monday, the names of all the different groups. But the halogens are group 17. As you're going down the periodic table, is it getting easier to gain or harder to gain? As you're going down the periodic table, is it getting easier to gain or harder to gain? Harder to gain. So as you're going down the periodic table for non-metals, it's getting harder to gain, so reactivity is going to decrease. And as you're going across the periodic table, it's getting easier to gain because the nucleus is getting more positive, has a greater pull on the electron, so it's going to increase. There's been so many trends that we've talked about today, and a really easy way to remember the reactivity relationships are if you think about the F's. So the most reactive metal is going to be francium, and the most reactive non-metal is going to be fluorine. Obviously, we would not include the noble gases in that because they don't react at all, right? Okay, so let's do a couple examples, and then I'm going to show you a demonstration. And I'll show you a little video of a demonstration as well. All right, are you ready? So which is more reactive, magnesium or barium? Very, very good. Now you should have known that even prior to this. How should you have known that already? What have you been doing all week?
We did that lab.
We did that lab. And isn't that what you found out at the lab? If you look at your data table, the barium had all positive reactions. The magnesium only had one, right? So that was something that you knew already. Okay, what's more reactive, titanium or zinc?
Where is
Titanium is 22.
What's more reactive?
Which is more reactive? Titanium.
Oxygen.
Right. By the way, in case you're worried, I will always ask you a question that's like this or like this. I will never ask you a question like this. Do you get what I'm saying?
Yeah.
Okay, they'll either be in the same row or the same column. All right, what's more reactive, oxygen or selenium? Oxygen. So I'm trying to trick you there because remember, before you decide which is more reactive, what question do you have to ask in your mind first? Is it right? Is it a metal or not metal? What's more reactive, silicon or chlorine? Chlorine is more reactive. Okay, very good. All right, ready to move on a little bit? Here's the deal. I will make a deal with you that anything else I'm going to say, I'm going to try to fit into that square. Oh, I got to show you these demonstrations. Okay, so think about the reactivity of the first group. You guys looked at the reactivity of the second group, which is called the alkaline earth metals. We're going to look at the reactivity of the alkali metals. Okay, so I brought to class lithium, sodium, and potassium. You know, it's weird to think of metals being soft, but they actually are. I'm having a hard time because I don't know that I can do this without my glasses, but we'll give it a whirl. In addition, I'm going to take, this is phenolphthalein indicator. We've used that before. Do you remember when we've used it? Do you remember what color it turns? Not yellow.
Blue.
Pink. Well, guess every color. You'll be right. Okay. So I'm going to put a little indicator in there. And so it's colorless. That means that it's either acidic or neutral, which it's just water, so it's obviously neutral. And I'm going to take out a piece of lithium. Okay, it is dull. When I cut it open, you'll see that it's shiny. But it's so soft that I can just cut it with this dull knife. Okay, this might be really dull. All right, and can you see, I don't know if you can see, but in the middle it's pretty shiny. By the way, what you can't see is that these metals are stored in oil, like a baby oil kind of thing, mineral oil it's called, for an obvious reason, which you're going to see here in a minute. Okay, I'm going to put it into some water, and right away you can see that it turns pink, it starts to fizz, and I'm going to put it on. Yeah. Okay. So you see it fizz. The smell gets worse later, so I feel confident doing it on my desk. So look where I did. I did lithium. The next thing I'm going to do is sodium. Wow, this is a big log of sodium. Okay, keep watching. Do you see it started on fire?
Yeah.
Good thing I have my goggles on. Okay, the third one, when we buy it, this was a brand new jar. It's so, oh! I'm thinking of the liability with recording stuff, but anyway. Good thing I put it
What are the other chemistry teachers?
Yeah, I'm out the window. Okay, take a look at the periodic table. So I did lithium, sodium, and now I have potassium. I just opened this bottle, and all it has in there is 3 little pieces. Let's do this under the hood just.
All three of them are last.
Yeah, just go all through.
And did you see that caught on fire right away?
Does that mean it'll explode faster?
Are any of those what? I still didn't.
No, nothing.
Okay. Now, you know how if you subscribe to different YouTube channels, you get little announcements about stuff? It was such a coincidence. Yesterday, I subscribed to, of course, Play-Doh Princess's channel.
Dang, that's dope.
Yeah, yeah. But then I also subscribed to this periodic table channel, and I just got an email saying that somebody tried this in 7-Up. And actually it was a college professor who couldn't even explain what happened. I could have done this out, I didn't did it.
It looks like,
It does, okay, so it looks like Mountain Dew, and I am gonna do this under the hood because, really made me cough this morning. I didn't have any 7-Up, I just had Sprite. I'm not putting phenolphthalein in there.
it's like thin.
And I'm gonna take a little piece of lithium. Again, the college professor could not explain why this happened.
What are you? Are you
No.
vaccinated?
But thank you, Will, for thinking that there's any that I
Oh,
could.
yeah.
Again, I didn't put any phenolphthalein in there. I'm gonna put this under the hood too.
Hey.
This is not as exciting, but you guys all agree it's colorless, right? We're gonna let that go for a minute. And it's really weird, it turns yellow like Mountain Dew. So what they are proposing on this YouTube channel was it actually forms an indicator. And why they think that is, the reason that it makes us cough is it forms a hydroxide. So sodium hydroxide or lithium hydroxide. Well, it's very basic then, hydroxides are very basic. Well, if you put a little acid in there, it goes from yellow to colorless. And then if you put more, so it seems to somehow be forming an indicator, which I don't know why. But we'll keep an eye on that. It's not as exciting, it doesn't catch on fire or anything like that.
What if you put the other metals in that?
So the YouTube channel said only do it with lithium. So I'm gonna trust that that is true. But what would be cool, and I did do this in college, to take a whole big chunk of sodium and throw it into a pot. So I'm older and wiser now, I wouldn't do that, but some goofballs.
You do it in the pot up front.
No, it's really bad. Just think about it. It makes us cough, right? It makes us cough because it produces such a strong base. Well, what would that do to the fish and the plants? It would kill
They're already dead.
everything in there. Which is why these jamokes that are in the video were kind of down to do this, but I'll show it to you anyway.
Oh, I think I saw a video.
There's a lot of them on YouTube.
Can we watch one with Cecil?
It's so sick.
Log it out. I'm recording it. And here's those. Oh, Trevor.
I do.
I don't. I will.
Trevor.
Hey.
We are recording. Hold on. Wait.
The cinematography is not great.
I don't know what you're talking about. That's not the one that I
Oh, it's
saw.
making me dizzy.
It looks like there's.
Plus, he has it in his hand, which is really dumb.